Much. So thank you very much for giving me the opportunity to talk a little bit about our hardware and software product in NVIDIA to this particular forum. Um, some of you in the audience may have seen some of this material already, um, some not. I already shared the slide. There are other links in the slide that you can follow up on some deep dive. And, um, and today I'm going to try to focus, since this is the Computer Accelerator Forum, more on the compute side of things in NVIDIA, which today means both CPU, GPU, but also software. Software is a very important aspect on it. And I try to give an update about the latest thing that we built and put together, and at the same time, try to give an idea through this update, the direction of travel that is really following in terms of where computing is heading toward and what the future may look like in the future. We recently announced in the past, let's say, 12 months, but also in the past literally 2 months, both our CPU product, our CPU plus GPU product, and our GPU product. So Grace Hopper no, sorry, Hopper is already for a while, Grace and Grace Hopper, and then Blackwell. And of course, we are committed in terms of a roadmap to continue to have a GPU only type of product, a CPU plus GPU product, a CPU only product, and also networking, etc., etc. But roadmap wise and future wise, nothing new will happen between now and probably a year and a half time. So speaking too much forward in the future, it's sometimes um, a risk in the sense that if you're familiar a little bit with NVIDIA, we have this common pattern of announcing a product and have it shipping in less than 6 months usually. And we're also kind of good in fast pivot following what are the market trend or the need of communities. So our roadmap is very fluid if we have to go forward in the future. But let's use today as an update of what we are, what we built, and how we see the next step, because it somehow gives an idea and a glimpse about also where the future is going to go. So there's a lot of content. I target to a little bit less than an hour. And I want to, talk essentially talk about the hardware part, a little bit about the role of AI, purely in terms of inspiration. I'm not an AI person. I'm a bare metal type of person, and that does HPC kind of stuff. But I will talk about the product, the hardware side, and I mean, some key update around the programming, which somehow glue all of them together. So we often refer to compute. We've been talking about compute for a very long time. We over refer compute as, the usual floating point calculation. It's now obvious, now kind of established in the community that there's a new way to do computing, to do scientific computing, and a new technique, let's call it the way, or new set of technique that we put under the umbrella of artificial intelligence that can allow us to do something different, sometimes something better, and allow us to unlock new capabilities in the type of simulation that we do day by day. So it's not anymore the usual. I run, I run a simulation on a computer and I get a result. There is this role of artificial intelligence to enhance and extend and sometimes even replace. So with this surrogate model, what is the classic way of do computing? And also there is the role of the edge, which you guys at CERN should be very, very well familiar since you operate a big essential experimental facility where it's not just the data that you simulate, but also the data you're able to ingest from actual real experiment that can enhance, complement, or somehow drive what are these simulations. So all of this is something that we try to cover with our software, our product, and we try to design tools and piece of hardware that allow basically scientists to touch on all these parts. So if we look at, let's say, at what is the, HPC and how AI transform HPC, also the way science is done today has changed considerably. So back in the days, we used to have, batch. So I launch a simulation and go away, coming back. Now more and more things are distributed, but also interactive. There's not just one simulation. Or now we are used to have, ensemble of simulation that are enhanced by AI technique. The role of experiment is very interesting. We used to capture data, analyze data offline. Now we're more and more interested to, do online kind of analysis. So online, sorry, on the fly kind of analysis, ingest data and processes as it comes. But also, for example, use this data to steer or control some of these experiments. And then, of course, we do offline. And then we all this grew together on this concept of digital twin, where you combine both what you observe, what you simulate, and the role of AI to glue together and help us moving science forward. I'm not going to talk about quantum computing. It's not really my thing. But it's also interesting how the programming models have evolved. Back in the days, we used to write code in C, C++, but modern scientists have, the choice is big. There's the usual way of doing things, and now we have, Python, Julia, these AI, um, these AI frameworks that are basically domain-specific languages by itself, et cetera, et cetera. So the world has changed. The role of hardware and software is changing and should change as well to consider all this new way of doing things. So especially on the I side, if we look about where NVIDIA is investing time and effort to build capabilities, we're going to talk about the hardware, but in terms of software, we build a couple of pieces of software and framework that are specifically designed to help scientists enter into this new era of new computing. One is Modulus, which is our open source, it's open source, I stress on that, open source platform for develop physical-based neural network and an artificial intelligence model, is essentially a framework. So it does not just plug into PyTorch. It allows to do data ingestion, data manipulation, loading, for example, CAD information from STL and other geometry, and also providing some building block and example how to design, for example, Fourier neural operator, PIN, normal DNN, normal CNN, graph network, etc., etc. So it's really a toolkit by its own. And we already apply these on a couple of big use cases that goes from energy, climate science, industrial HPC, healthcare, etc., etc. So this is very interesting. The other one that maybe someone has talked to you about in the past is what we call Holoscan, which is again, it's a framework, it's a toolkit that takes our CUDA essentially toolkit, our CUDA runtime and accelerated library, and package them in a way that are useful for those streaming and data ingestion, data manipulation use case happening in real time. And so use case would be, for example, when you have, you can take an example of your experiment. You can you can have a network card or an FPGA that push data through a pipe from your experiment and then hook it up through a network connection to a GPU accelerated system, and through this toolkit, getting the data on the fly, move it to GPU and trigger, execution of kernel, etc., etc. So this is really designed to be scalable across system, because obviously this can match the concept of edge, not just the concept of data center. So this toolkit does not just work on our, data center GPU, but also on the more kind of, it's called IGX, so our like a Jetson style kind of thing. It's more, and it provides a high-level API based on C++ and also Python to simplify the programming. And again, it's open source. He has his own AI inference engine plugged and bundled with it, etc., etc. And the whole idea is that I have sensor data, I have data that I ingest and I manipulate it, and you can use either computer or either AI model to do so. We've seen this applied to processing satellite data, healthcare imaging, instrument, etc., etc. So this is very important. All of this then goes to what is our platform for digital twin. It's called Omniverse, that will require probably an hour only by itself. Actually, there was an open lab event recently where there were a couple of talks, not by NVIDIA actually, but some of the people involved at CERN, and some European projects around digital twin, they were explaining and showcasing how this concept of universe could be used in high energy physics. Because I'm a console type of person. I would suggest to go check there and dive a little bit on that. But this is the kind of almost the last frontier for what we are today, where we try to bundle everything together and provide a visual and interactive view of what's going on, either simulated or on the ground truth, so in the real life. AI is big. AI is getting used all over the place, not just to do, cat versus human, like it was 10 years ago. The buzzword of the moment is generative AI. So this big model or foundational model that are allowed to basically provide, the first level of intelligence over a specific domain. And a big player in the industry moved, well, all started around large language model. But following this trend, big player started to look at other domain or a scientific domain, and we've seen emerging these foundational models that are more targeting toward things like, for example, biology, like AlphaFour, climate, or even material science. I'm not aware about, but probably there is, about any big effort around high energy physics or something related to particle physics, but it could be, but just I don't know. On this topic, because it's very topical nowadays, generative AI models are also famous because they require hundreds, thousands, or tens of thousands of GPU to train from the ground up. So from, let's say, from the first principle, from essentially zero. However, if we look about how you would build a foundational model, you don't really need a lot of GPU to be fair. Sure, you need a decent amount of them, but it's not like competing with the cloud to build the next chat GPT or the next Bard or the next whatever it is. Often, especially in the science domain, because of the size of the data, the type of the data, also the characteristic that you need to look into the data in order to make it qualitative good to do this kind of training model. What we have is that we start from a model that is being pre-trained or somehow even a LLM type of model that is being generalized using a different modality, and then look into retraining it, fine-tuning it, checking the model, etc., and then apply further optimization. All these steps, sure, they require GPU, but often can be done with order of hundreds of GPU and only few days of training rather than months. This is as a testimony that even in the area of AI, where the more GPU, it seems that it's better. There's a lot that can be done, especially in the area of science, with a modest amount of GPU, but with a good domain expertise. The tricks here is less technology, but more awareness about what the method are, what the physics or the science is, and then apply brain rather than compute power. We also need a little bit of compute power. So the engine that has been powering all of these other than just computer in the past, I think almost 1 year and a half, it's Hopper. So Hopper is the GPU we built essentially for AI. It's the first one we built with AI in mind, and it's the first one that contains a bunch of new innovation that are designed to speed up AI models, not just compute. We will mention some of those. It's a very big GPU. It's built with TSMC process, and it's still a GPU that you can find today in different form factor that has it is a monolithic die. So yes, sorry. So the H100 SM architecture is composed by this tensor core. This is the fourth generation tensor core. We support new form factor and is improve the programmability using something called the thread block cluster for people that are familiar with the CUDA and C++, but also the tensor memory accelerator, that is a piece of hardware that allows to move data in and out of the stream multiprocessor and the shared memory without the need to double copy on the register. And then he has a bunch of other characteristics, that are based in there. Sorry. So it's also interesting to notice that Um, the Opera as a GPU is a very beefy GPU. Compared to 10 years ago, what happened is that we find ourselves to have a lot of more compute power compared to what was a GPU 10 years ago. In 10 years, we probably went 20, it depends how you compute the flops, because if you do single, double, or tensor core, but we move from a factor of 20 to a factor of 60 time of performance. So everything that we've been done around software was about find a way to exploit the parallelism and the power of the GPU at its best. Because the technology from another perspective moved very fast, but often we're dealing with software and problem that do not expose a level of parallelism that can fill such a big GPU. Um, sorry, sorry guys. This, why is doing this audio? Apologies. Let me, there are recordings on this. Sorry. Okay, so let me go back. So sorry. Let's see. Someone had. Hmm, I don't know what's going on. Okay, let me try anyway. So let's talk about the H100. We skip the slide that we stay in the PDF. So H100 is our flagship GPU, as I mentioned. This is the so-called SXM form factor, and is the form factor that we bundled together in the 4-way and 8-way HGX system. And as I mentioned before, can have up to 80 or 96 gigabytes of memory, HBM3, and is available by various OEM in various form factors. So this is our current one. We also have another type of GPU that is kind of less popular, which is called the L40S. It's based on the ADA architecture. It's like a small sister of Hopper. And this was essentially designed, yes, for data center, but really more about AI compute, especially training and inference as well. So, for example, Opera has full support of FP64, so can do good AI, but also good compute. L40S does not have the same FP64 capability. However, if you need to do rendering, ray tracing, AI training, or AI inference, this is perfectly fine. And the fact that it is a PCIe form factor means that it's much easier to put into server and to have big server with a lot of them. From a portfolio point of view, so we have the H100, we look at the data center, good for real training, real inference and compute. The L40 is good enough for, on a lot of use cases. We still have a very small form factor that allow to put into, that are specifically for training, specifically for inference and for video processing and edge computing that can go into server at the edge. So they are very power efficient and small in form factor, but obviously the capability is not as good as a full data center GPU. And so these are still available. These are still used all over the place. That's perfectly fine. Now, the news around the Hopper was actually the creation of the Grace Hopper type of architecture, which I work directly on and I'm more familiar with. So we decided for multiple reasons, including the lack of proper PCIe connection, the necessity to drive energy efficiency, and also to add extra capability when CPU and GPU work together to build this platform and to first start to build our own CPU and then build our own CPU plus GPU type of platform. So we create this super cheap super cheap platform where we have either a CPU plus a GPU or two CPU. We call the CPU Grace, and we base Grace on the ARM architecture. So the Grace super chip is essentially this iPad size type of mini board that can be plugged into a proper motherboard into a server, which contains both the CPU, two SoC in this particular case, and has also all the memory and power regulator and I/O, etc., etc. So it's like a mini computer by itself. It's all integrated into the board to make it very energy efficient. The entire board consumes around 500, 550 watt. He has two sockets, as I mentioned, with ARM Neoverse core. Neoverse being the generation of ARM core that are designed for the data center. For reference, Graviton is V1, Graviton 3, sorry, is V1. Graviton 4 is it's going to be V2 as well. And yes, it's on cache. Obviously, in terms of memory, it comes with a different SKU. At the moment, we are in production with the 480 gigabyte SKU, which is roughly 1.7 gigabyte per core. But we're going to have by the end of the year a 960 gigabyte capacity, which brings 4 or 5 gigabyte per second, gigabyte per core, something like this, of capacity. The memory is soldered on the board, so can't be in this generation extended. And it's based on LPDDR5X. It's an interesting choice because it brings bandwidth comes from the memory controller. We're gonna check them. There's no secret. There's no magic. But from a power point of view, this is a very efficient type of memory. Usually, if we look at the overall industry, including mobile and client, this type of memory comes without the error correction, but we work with the memory provider to add it. So we have a memory that is fully fledged and good for the data center. What's good here? The whole module is really energy efficient. Now, where we see Grace winning, when we see Grace being positioned and used, obviously we build it for high performance computing and large language model and large AI training. So it's great to do high performance tasks. You can perfectly run on Grace also databases, process videos and images, even gaming, like game server, etc. Thanks to his good balance between, the internal NOC bandwidth, the memory bandwidth, the integer and the floating point performance, and also the floating point, the performance per watt. So it's very good as well in what we consider the traditional consumer and traditional data center workload. Let's be honest, you can run web services or very lightweight services on Grace too, but because the number of cores between brackets only 144, we don't see Grace being, the best CPU for what we call it the front end, so like where we need to have where the number of core actually matters more than how much strong a core is. So yeah, so you can buy Grace to run just web services, just a little bit of a waste of compute power. But that's where we see Grace working. It can cover all the use cases anyway. Grace, it's very important, especially if we want to go through the exercise to bring up a system without the pain of managing too much exception and weird hardware. Grace is a fully compliant SBSA platform. In the ARM ecosystem, we have this ARM server ready program, which basically says if your CPU is certified with this kind of system ready certification, it means that it complies with the whole set of standards that allow UEFI to boot, things like that. So PCI detection, essentially all the OSs that are ARM ready or also ARC64 compliant will boot on Grace no matter how old they are or new they are, which is very important. It gives whoever has to deploy system the confidence that it will work out of the box. And obviously, the system vendor also go through some level of certification in that step in this regard as well. Grace per se, because obviously we build the CPU, people are asking about the performance. It's always important to bear in mind that Grace was born not as a flop engine. If you want flop, we have GPUs for that. Was born primarily as a data mover, as a companion for the GPU. So in several of today architecture, in CP6 architecture, obviously, what you often notice is that you either have choke points in the network on chip. So when you would love to drive more bandwidth, more I/O, but simply the CPU cannot cope with it, or you have enough bandwidth or a good level of bandwidth, but the chiplet or the multi-die architecture of the CPU basically makes the pain of pinning processes something that some people do like, other people who love to not care about. So we build Grace with this idea of being a data mover. So it's a single die, very flat, with a very strong knock that we build our own. So this is not ARM IP. And we built inside the chip a lot of memory channels to drive a lot of memory bandwidth. And obviously you have everything you expected to see, meaning PCIe Gen 5. Um, and in this particular case, we have a specific link called C2C that allow to connect Grace to another Grace or Grace to Open, which we're going to talk about that. So if you boot a Grace only system, which is going to be very interesting for a lot of use cases that are not accelerated or not accelerated enough, you're going to have a system that has better power, better performance versus power, um, only two NUMA nodes because we have two dies, but a very big bandwidth between the two. A fair amount of RAM, obviously cannot be extended, but it's a fair amount of RAM, and all of these in 500 watts. Competing platform might have more memory capacity, which by the way, DDR, normal DDR, the more you put inside the system, the more consume power. And you might have CPU with multiple chiplets, so you have to deal with the NUMA fragmentation more explicitly. But even if even in this scenario, really the power is what can be a limiting factor. Today we observe that today when we speak with customer, often they run out of power before running out of space. So power for system today is it's very important. Now, a little bit of number, but the idea here is that independently where you position yourself, Grace is never going to be like 2 or 3 times faster than competing CPU. That is not what this design is for. What is interesting to observe is that if the gain is very little, and sometimes you say it's not enough to justify me to change one into the other, it consistently beat in energy to solution competing platform, which is what was designed for. Grace is good. We take one of the two Grace and we swap with Gopper and we create the Grace Hopper Superchip of GH200. We have only 72 cores because we have only one Grace die. And then we have the GPU. The GPU in Grace Hopper is exactly the same as the one that I presented before. Just have more memory. It's the same die. It's the same architecture. We just use 6 of the HBM side rather than 5. And so we move from 80 to 96 gigabyte of memory on board. What makes this special is essentially this C2C link. This machine, and I did a talk with more in depth on the architecture. This machine join and unify CPU and GPU. It creates the illusion, it creates the illusion of a single unified memory space. But the reality is that you have one physical memory for the CPU, and we pick the right memory for the CPU. We like DDR because DDR is good for low latency, deep cache hierarchy, so anything that is very latency sensitive. And we pick up HBM on the GPU side because latency for HBM is not great, but it can drive really high bandwidth, so it's good for this kind of high throughput engine like the GPU. And we make them see each other through this C2C link that realize cache coherency between these two engines, giving the impression that is a single memory pool, but keeping them separated so we can add more capacity on the other one, innovate on the other, and use the best of both worlds at the same time. The C2C, as I mentioned, enables this level of coherency. Also, it's a very efficient bus. And the reason this is the case is essentially, it's essentially two. It's not, it's essentially the way it's built. Okay. So the way it's built, the IP of this bus and the way you talk to the GPU, but also because it's physically one is next to the other. So the bus itself only travel 2 to 3 millimeter between the two die. And this also has strong implication about how much energy you dissipate because of the wiring and things like that. Through this bus, Grace Hopper implement something that is called AST, which creates this unified memory virtual address space, which essentially means that at any point in time, the I/O MMU of the CPU, the I/O MMU of the GPU, which are the piece of hardware that are responsible to translate virtual to physical memory addresses, are able to read one single page table and immediately figure out where the data is. Then through this link that speak a protocol called CHI, which essentially is the same protocol of the CPU NOC and the internal part of the GPU, allow one engine to read and write the memory of the other directly, which is very powerful. The integration of the super chip, the integration of CPU and GPU in the super chip also enable us to do a couple of other things. One of the things that is important is this idea of automatic power steering. I don't have this slide, I realize, which basically says if I set a power, if I set a power endpoint like a kilowatt, this is the maximum TDP of the Grace Hopper on the super chip, and I need more power on the GPU, the power automatically shifts on the GPU when the GPU is under load, and then go back to the CPU when the CPU takes over. So obviously you can decide to operate at less power if this is, for whatever reason, you are power or constrained. But these allow to move power and give more power to one engine or the other based on where it needs it. So for example, if your GPU does flops or does big matrix multiplication, you want to pump up the GPU frequency so you can actually push more flops, you know, out of the GPU. This power steering capability is driven by the GPU. So when there is GPU load, you suck the power and go faster. When the GPU is less load, means that the CPU is probably doing something else. The power gets renormalized, etc., etc. And through this concept, then people can go and check how to do application power tuning. So you can always set as a user, for as long as you get the right permission on the platform, your maximum power for the super chip, your maximum power of the GPU, and then shift the power accordingly. And we have seen Grace Hopper being able to shine and provide great capabilities on a wide range of workload based on its characteristics. So if you still have partially accelerated application, which is, let's be honest, a good majority of the application out there, you can be benefiting from a fast memory bandwidth on the CPU, because if you have flop, you move to the GPU. But if you still have something back on the CPU, most likely is memory bound. So faster CPU give you a boost. If you have application that do require to move big bulk of data from the CPU to the GPU often, either for I/O or just for compute, the C2C, which is like 7 times faster than the PCI in terms of bandwidth, will allow you to move data even faster. And then this whole idea of extended GPU memory or peeking into each other memory can unlock some new use cases, which can be cataloged in two ways. You just access each other memory without trigger a CUDA API. So your benefit is I don't have API latency to take into account. I just read what I need. Or, for example, for some of the AI framework that does like RAG or embeddings, so some of these AI frameworks that are very demanding in terms of memory footprint, you can do the so-called reverse offloading. So you store a lot of data on the CPU, you never move into the GPU, or you move it very, very rarely, and you access it when you need it through the C2C, less speed than the HBM, but still good. So it's still at least 500 gigabyte per second. So this was the product. What's come next? So in terms of product design, we took the Grace Hopper form factor, which is a one-to-one, and either extended it. So we added HBM3E, so it means more bandwidth and more capacity. This is just like a small change in the HBM side, but nothing in the form factor. And then we build this NVLink Dual GH200, which are two of these glued together. You're gonna see how they look like. These are platforms that, so these form factor are all into a system, a server form factor called MGX, which is a design that we see adopted by multiple OEM, ODM, and it's something that can go, in the normal data center. You just need to have a rack with enough cooling, and most of those are both air cooled or water cooled, but also air cooled. So the dual GH200 is this the diagram of the dual GH200. The interesting bits is that in one single system, now you have both a Grace and basically two Grace Hopper SKU. The Hopper are connected with NVLink, so maximum exchange between them, and the Grace are connected with additional coherent NVLink, coherent CPU link. So these are different than C2C. The speed is actually very different. So maximum speed between Grace and Hopper with the C2C, but then you essentially see like an SMP mode, 144 core and 2 GPU. And then you scale out, adding InfiniBand network or Ethernet network, whatever it is. Now, the good thing about having the C2C, AST enabled, and this NVLink between the GPU is that you can start to access memory in a very interesting way. So if you are a process on the GPU and these two GPU have segment of memory register between each other, so it means that they can exchange to NVLink, you're not only able to read and write on the other GPU memory. So this is let's see if I can see the orange part. But from the GPU, you also be able to read and write on the CPU memory of the remote node. At in this case, your limiting factor is the memory bandwidth here, 500 gigabit per second. Because this link is 900, this link is 900, so it's more than enough to sustain full bandwidth from here to this memory. This is very interesting because it allows to really almost extend the memory of the GPU from a GPU process point of view to the entire system. And in a system with multiple of those, and we switch to multiple nodes. I've been very careful to say that this is possible if you start from the GPU. If you start from the CPU, you only see this part. This is the way the architecture is done. For HPC specifically, we also went slightly further and we built this quad GH200 node architecture. These are very dense. These are only liquid cooled. Because they're very dense and liquid cooled, they don't operate at full TDP. Different vendor operate at different TDP. HPE around 650, 670. Evident can go slightly upper 700. And where instead of having two per node, you have four per node. So it's very, very dense. The side effect of this very dense solution is that only Eviden and HP has designed a board that can handle one or two of these quad modules, and it's very dense. The blade form factor is very custom, and a single blade can burn up to 8 to 9 kilowatts. So it's a big investment, but it's a big piece of hardware to manage. Why this is relevant? We are going to see in the next by the end of the year, so in the next 6 months, several Grace Hopper J200 supercomputing coming live worldwide. We have Venado in the United States. We have Kaust in I don't remember the name. Kaust in Kaust in Saudi Arabia. We have Isambard AI in Bristol, and we have Jupiter in Jülich, which will be the first exascale system in Europe. So the first exascale system in Europe will be based on this node design. They're gonna go multi-node either with Slingshot for HPE or InfiniBand with Eviden. This was, the platform that we have today. How we program them, and especially how we program Grace Hopper, since it's a kind of a new thing. A narrow CPU, new GPU with capability and cache coherency, etc., etc. So from a programming point of view, aside adding extra feature, bug fixing, and continue our journey to support standard languages, we've been faithful and strongly anchored to our strategy of supporting multiple programming models. We are to a point where you can pretty much pick up whatever programming model you want on GPU, and most likely it's going to work on NVIDIA GPU. We supported three key categories. CUDA, obviously, is the way and it will continue to be the way to squeeze the GPU, up to its very best, what we so-called the speed of light. And it's where we bring innovation, where we bring, all the right API and capabilities to really go and tap into, the tensor core, the transformer engine, etc., how you manage the memory, all this kind of stuff. In the past few years, we went really big on standard languages, which is essentially the idea of you don't really write anymore a GPU program. You write a parallel program using parallel constructs that are part of the language. stdlib in C++ or some of the do concurrent and array notation in Fortran, for example. And if you do that, you have a code that doesn't look like yes, GPU code, but through some, between brackets, compiler magic, you can essentially offload to the GPU. There's a lot behind of this concept. Obviously, there's a lot of work on compiler engineering, but also there is something called a unified memory, which is in NVIDIA term rely on the fact that CPU and GPU understand where each other memory is. They can migrate memory from one to the other when it's needed through essentially a page fault mechanism. So far, this was possible in software on x86 plus GPU. It was working, but because it was in software, there was a lot of um, drawbacks, and sometimes the developer experience was not great. Now with Grasshopper, a lot of the complexity around this has been simplified by supporting into the hardware, and so the overall developer experience, increased considerably. And in between the two, we still have directives. Whatever we like it or not, whatever you are in the OpenSCC versus OpenMP camp, I honestly stopped caring. They are both work on NVIDIA GPU. They are different, obviously, but they both work. Directives are still proven to be an effective way to move big code bases in a very effective way from CPU only to GPU. Because the one on the left, the ISO standard languages, really rely on the fact that you write a modern code base, not everywhere is there. And the one on the right, CUDA, I take the critics that is basically a vendor lock-in. If you don't have CUDA, you cannot do much about it. So these are the three pillars, and we continue to work on those. The one that you choose, as I mentioned, is about if you value more control, if you value more performance, if you value more productivity. So it's up to the developer to choose what's the right balance. The latest thing that we've been working on in software on our SDK can be summarized in this slide. We really started 6 months ago to add more and more on the C++ support, C++ 17, C++ 20. So we added, for example, coroutines, and we added the send and receive proof of concept, which, based on my knowledge, is not fully ratified in the C++ standard yet. But because of Grasshopper, we also add more support on building for ARM and this unified memory cache coherent integration. So unified memory support and things like that. We added our domain, we added our mathematical libraries. I will talk about it. And as I mentioned, we keep improving across all programming models. We release this very often, so it's very difficult to keep track about what's getting all the time. From I don't know if it's relevant for this forum, but for scientific computing in general, we've been investing a lot on multi-node accelerated library like QFFT-MP, QSolver-MP, and QBLAS-MP. This has been required by a lot of scientific codes for a very long time. And this bundle, come all together, and it's also it's free, by the way, so it's free to download. It released 5 to 6 times a year. It supports x86 and ARM, and it contains essentially both the compiler, the libraries, the API, and some of the tools like debugger and profile. On the ARM side, which is the new part for us because of Grace, how we position ourselves and what we do. So we've been investing, we are continuing to invest in the future to enable the broader ARM ecosystem. Because we are the first RV9 SoC, we are the first one pushing into the public patches and enabling software to run on this new architecture. Other will come and follow us. On top of this, everything else is pretty much specific to NVIDIA. So up to the optimized OS and vendor software, the new compiler, the, the basic software that you will expect to see in a Linux box to run, all is in the public, all it's useful and portable to other ARM SoC. When we start to pair up the GPU, then we have our own stack and an optimization for GPU computing. In terms of compiler that are the most important entry point, we do contribute into LLVM and Clang directly. We do maintain ARM support on our compiler. We started to contribute into the GCC, even though it's a little bit more complex than other compilers due to licensing, but we started to make a step in that direction. And by doing so, we have essentially a variety of choice of compiler that allow people to basically pick up whatever they prefer. Mathematical library is the next one, so usual stuff that people will expect. Another thing that people expect that are into coding is enabling tool to essentially understand performance and performance counter low level for Grace. So we started by enabling our tool because it was easier, but then we are streaming to Puppet, and we are working with third-party tools to get them fully support Grace. So in the near future, we're gonna see a full ecosystem enabled from a developer point of view, compiler libraries, performance tool, to just go and build on Grace for maximum performance. In terms of programming model, what's new in the Grace software architecture is this ability that is on the right to have the system allocated memory. So rather than migrate memory where it's more convenient based on who is using the memory at that point in time, either explicitly or automatically through managed memory, the system allocated memory feature allows to leave memory on one side and use and access in read or write mode from the other side. This strategy this strategy follow the first touch principle. So you don't touch first, you're gonna stick to it, and then you access from the other side. So on CUDA, we have the usual API to move data, but if you use system allocated APIs like malloc or CUDA malloc manage, first touch is where the placement actually matters. So if you do a new or a malloc on the CPU, but you first touch on the GPU, the physical GPU will be allocated on the GPU side, and you access it through the C2C. On the other end, if you do the allocate on the CPU, but you first touch on the CPU, the physical CPU happen on the CPU, and the GPU kernel will read it through the C2C. We read it directly on the CPU memory in read and write mode. So this is what the power of the C2C. Due to time, I don't have codes to show, but there is, as I said, on the open, I believe in the Open Lab event that I did 2 months ago, I showed some of the code that showcase how this actually in practice work. Nothing breaks in the previous mode, but this new mode can be very powerful for certain use cases. If you are into standard languages or directive, you don't really use CUDA API to manage to move data. So we extend our compiler to use a new mode, it's called a unified, which basically allow the access of data structure on the CPU, even if they're not managed. So in the normal scenario, let's take OpenCC, you explicitly move data, from one side to the other. So the two memory spaces are separated. When they are managed, the dynamically allocated data is automatically migrated based on when you touch it and when you need it. So this is happening behind the scene, but obviously global variable, stack variable, things that are outside this parallel region are not accessible, essentially, cannot be accessed. But with unified, which by the way can be managed or not managed, but with unified, you can really access all data on both processors, no matter what. And this is also what's new, what's hardware supported in Grasshopper, and what could be emulated in software using HMM on other x86 GPU. So, Hopper, Grace and Grasshopper, a little bit about what's new in terms of programming model over there and our commitment to push, for example, standard languages. Um, we already announced literally a couple of months ago what is the next generation GPU, which is called Blackwell. Now, Blackwell is a different beast compared to Hopper because we specialize this GPU really for artificial intelligence. We didn't witness an explosion of AI model, uh, also in terms of variety, also in terms of dimension. Now we're talking about trillion of parameters, which is, I think is ridiculous. I can't really imagine it. It is really a lot of parameters. And the big hyperscaler, the big CSP, they're all training from scratch. They're all fine tuning. They're all refining and push the boundary and innovation on this big generative AI and large language model. So to tackle and to handle these type of use cases at the most efficient way, both in terms of time to solution, both in terms of energy to solution, we build essentially Blackwell, which is literally a GPU for AI. You can do everything with it, but it's specifically for AI. So everything that we've been done in it, in terms of, for example, NVLink, in terms of transformer engine, in terms of new precision, is about the AI use cases. It's also the first GPU that we built with a multi-die type of approach. We need a lot of state, we need a lot of silicon. So we pair up with TSMC to build this um, dielectric, dielectric technology to build two chiplets together and realize a single GPU. And by doing so, we've been able to add more HBM sites, which means more memory bandwidth, also more memory capacity, and also realize essentially more compute power, more streaming multiprocessor. The transformer engine that we extended, so operate the first transformer engine. The second transformer engine is all about even reduced precision. So now we support FP6, FP4. We support a variation of FP4 with a different mantissa and exponent variable. And we double down on the throughput for the integer. So we can cover not just training, but also inference. Inference is a big thing for the future. We often refer to AI as I'm gonna training this big model, but the reality is that once you train it once and you're happy with it, you just need to do inference with it over and over again. So we designed this to also cope with integer precision for inference use cases. It's interesting that if we start to analyze the trend in the models, in artificial intelligence models, so how big they become, how complex they become, how many parameters they have, clearly they will never fit in a single GPU. We will still need to have a lot of GPU to store them and train them efficiently. And you can have data parallelism, you can have pipeline parallelism, you can have model parallelism. There's multiple techniques, but it looks like this mixture of expert models that are very trendy now, they have specifically a communication bound. So they really stress the communication in and out the GPU more than before. So on this Blackwell, we pair up Blackwell with a new generation of NV switch and NVLink, essentially, new NVLink and NV switch. So it's a new chip that essentially, I don't remember how much is in terms of ratio, but it essentially increases even further the ability to drive all-to-all bandwidth between group of GPUs. And we use this as a building block to build a couple of things. We have the Grace Blackwell 200 super chip, which compared to Grace Hopper is not a 1-to-1 ratio anymore. This is a 1-to-2 ratio. And this 1-to-2 ratio is really because we want to stress on the GPU capability. We take this super chip board, which if you were to power it in full is around 2.3, 2.4 kilowatt. It's a little bit power hungry. So we put it into a compute tray Okay, and because of the density, this compute tray is going to have you know, it's going to be a liquid cooled. There's no other way to put two of them in a single U. Then we have with this NVLink switch tray, because we need connectivity out of this tray to other trays. InfiniBand is good, but InfiniBand doesn't have enough bandwidth to train this model at full speed. And then what we build when we put them together in this rack form factor, which we call the GB200 NVL72, which is essentially 72 of this GPU fully connected with NVLink in a single rack. This is more than 100 kilowatt rack. This is all water cooled, so it's going to be very heavy as well. And this is not the type of hardware that we see being deployed everywhere. But the next wave of artificial intelligence, generative AI, large language model innovation will be most likely powered in the cloud with this type of rack behind the scene. But we don't build just that. So Blackwell as a CPU will be paired with Grace, but we will also have HGX. It's going to coming toward the end of the year. The GX B100, is going to have a certain memory capacity. The GB200 is going to have a slightly more power and more memory capacity, but same compute. And then we're going to also have, I don't have a slide, we're going to also have a B40, which is the PCIe version. So Blackwell is going to be in different form factors, but these are the ones that we're going to see in HPC AI factories or in the cloud to drive this new generative AI large language model race. Yeah, there is some performance, and we already saw a lot of partners interested to either build the one in the middle, so the rack scale, or the HGX form factor. In the upper generation, we have the 4-way as well. So we have PCIe, obviously, 4-way upper in SXM form factor, and 8-way, the DGX-like type of box. For Blackwell, for a multitude of reasons, we decide not to pursue the 4-way. There's going to be PCIe that can be connected with NVLink into like a bridge, but still PCIe form factor. And it's going to be 2 or 4. This is maximum kind of pairing you can do in a PCIe form factor. We're going to have the HGX B100. All of these will have NV switch in between for full bandwidth between GPUs. This is going to be great to train in the AI. And then this NVL72 is going to be really top of the spear for people that need tens of thousands of GPUs to train trillion of AI models. And that's pretty much it. What comes next? As I mentioned at the beginning, there will be a Grace Next CPU. There will be Grace Next CPU paired up with Blackwell, and then there's going to be a Grace Next CPU paired up with Blackwell Next. So we have a roadmap that mix the two going forward. Our Grace Next is going to happen at some point in 2025. And for the next generation GPU, well, we just announced Blackwell, so it's going to take a little bit more time. But we usually keep a 1.5-year cadence, so you can just do the math, set the reminder in the calendar to see when probably the next one is going to come out. So this was an overview of the compute and accelerators kind of product portfolio and what we just recently announced and what comes next. Apologies for the glitches of a couple of slides that I borrowed from a colleague of mine, but you'll check them. And but I'm happy to take some questions in the next 10-15 minutes. Then I have to go pick up my son, otherwise my wife is gonna chase me.
Excellent, Filippo. Thank you very much for the very, very nice talk. Are there any questions? Yes, first one, Attila.
I don't see the chat.
Yeah, Attila, please go ahead.
Yeah, thanks a lot for the presentation. So I was a little bit surprised by then you were talking about the memory management on Grace Hopper and how we should be thinking of how memory can be accessed from the CPU or the GPU. Now I got a little bit surprised because I thought that even with standard like CUDA malloc and CUDA host malloc allocations, it would be possible to cross-access GPU and CPU memory on Grace Hopper. But from your next slide, I think, I got the impression that is that only possible with NVHPC?
Oh, no. So with CUDA, you have total flexibility. Okay.
Yeah.
So with CUDA now you can essentially do three things actually. You can have the so-called system allocator and CUDA manage, which allow placement based on first touch. So it doesn't really matter which allocator you're using, based on where you touch, it goes on one side or the other. But because these two memories are separated, okay, they are separated physically, you can still decide that you want to have something that is only on the CPU and you cannot access from the GPU, and only on the GPU and you cannot access on the CPU. So CUDA device memory is on the GPU, but is not accessible from the other side, and vice versa. This is done mostly to maintain backward compatibility with previous models. So nothing breaks, but if you want to manage this cross-link, you just allocate memory and let the system essentially allow you to pick on the other side and the other.
Okay, but I think I understand. So in the past, I thought that even if I would allocate memory with CUDA malloc specifically on the device, I might still be able on Grace Hopper to just directly access it from the host.
Yeah, you can do it with which API you're using? Sorry, the host malloc hoster or which one are you using?
So I think I understand the setup now, but I thought that on Grace Hopper, I would be able to allocate memory specifically on the host or specifically on the GPU. And as long as I was happy with the performance hit of accessing memory from the wrong place, I would still be able to access it, across the device boundary. But now I understand that as long as I use CUDA malloc, that will still only be accessible from the GPU.
Yes, specifically CUDA malloc, yes, only on the GPU.
Okay.
That's
and that should be fine. That should be fine.
This is the way it works.
Okay.
Okay. Thank you. And we have, please.
Go ahead.
Yeah. Hi, this is Severin. I have a question regarding the precision performance, because the latest GPU architectures are really AI driven, so they're really cranking up the performance on low precision and even lower precision. I'm wondering if there are still improvements in FP64 or 32 to be expected from Blackwell over Hopper, or if in the future we might worry that FP64 might even drop in performance because it's not relevant to AI anymore. Could you please comment on that?
So there's only limited state on the GPU. So putting FP64 on the GPU require, silicon space, but also require power. And for AI, we made the choice of decrease the capability of the FP64, FP32 to basically advance this more reduced precision. So it's not that they don't exist, but the ratio between how much flops you can push in FP64 and, for example, FP16 is huge now compared to between Blackwell and Hopper. But it's still supported, so it's fully compliant anyway, just less throughput. It's less throughput to a point that if you compare the two datasheets, there's really no improvement in FP64, probably even slightly less compared to Hopper. Despite on other precision, Hopper is way faster. Sorry, Blackwell is way faster. So it's AI GPU. We've been very upfront with that. You can run FP64, but don't expect, a speed up in this scenario. Now, that does not mean that you cannot use this precision to do something else. And also, that does not mean that we are completely drop FP64 forever. We are very much involved in scientific computing. We are very much involved in HPC. Hopper still exists and is still a very powerful GPU to do FP64. And now we live in a time where we have both products and people can choose if they want to do more of one or more of the other, more on the HPC or more on the AI. Hopper is good for AI as well. By the way, it's not bad. It's just not as fast as Blackwell. But at the same time, you don't want to buy Blackwell only to do scientific computing. That's the wrong GPU. So you can still buy Hopper from that point of view. Future. For the future, there might be specialization. There might be some specialization going forward. Again, because the real estate on the GPU and the capability that require us to be at the forefront of AI and AI capability require us to specialize silicon more on one side versus the other. I would not be worried about us dropping FP64. This won't happen. But it's too early to make any comment about future product and what will be the FP64 ratio. I just want to, I will leave it by email to the organizer, then they can share the link to the audience. There is a paper published by Tokyo Tech that can demonstrate how you can run a DGEM using integer. So, do you need a FP64 ALU to do a FP64 arithmetic? I'm not 100% sure, to be honest. So there is a whole area of research and activities about how to use other precision to emulate FP64. And I suspect that this platform will fuel some innovation in that mixed precision emulation kind of area, maybe out of necessity, but just because integer, for example, on this platform is stupidly fast. So we'll see how it goes. At present, we build it for AI in mind. This is the reality. We're not really shy about that.
Thank you for this very elaborative answer. Just one last point. You said that FP64 might be a little bit reduced on Blackwell. What about FP32? Because we might even work with that.
Similar. They're similar, but they're depenalized, both of them, from that point of view.
All right. Thank you very much.
There is the datasheet online. I just don't have the slide with just a lot of numbers. But you can pull up the datasheet of the H100 and the B100 and see, and see the ratio.
Thank you.
Thank you very much. If you could send me the link to the paper, that would be very nice. I put
I
put it on the agenda.
It is done by Tokyo Tech, by...
Okay.
I'm gonna send you the paper, yeah. It's published on
just later. Yeah.
Public stuff. Yeah.
Perfect. Thanks. Okay. Attila, you have another question.
Yeah. I have a different one as well. So ARM CPU profiling. You mentioned that the standard NVIDIA tools will be able to nicely profile Grace CPUs as well. To be a little bit, maybe provocative here, since I imagine that a lot of us will be optimizing our code for different ARM chips going forward. Will these profilers also work on other ARM architectures?
So yes and no, meaning they do work also now. They're like a Ampere Altra or Graviton. It's not a problem. The reality is that if you want to optimize only for CPU, you don't want to use this tool. I show this tool because this tool is good, because it shows also the GPU side of things. If you only target CPU, you probably want to use HPC Toolkit, ScoreP, Scalasta, whatever it is.
Okay.
The bottom line is that these tools are built on Puppy, essentially. So they see the performance counter that enabled the Linux kernel and accessible with API through PAPI. And starting from PAPI 7.0.1, we enable the ARM Neoverse V2 core. So every CPU that is built with the ARM Neoverse V2, either Grace, Graviton 4, Google Axion, no, Cobalt is a different one. So there are a bunch of CPU that are coming up in the next, let's say, nowish or imminently, generally available that have this type of core. And so we are compliant with the 1,500 pages of ARM specification for that core. So for as long as any open source tool have a latest, can use the latest PAPI, you can see the performance counter like number of SIM distraction, number of cache misses, this kind of stuff. Now, there is only one thing that is not yet available in the open source, which are what we call the out-of-core counter. So, as I mentioned before, we build Grace using the core of the shell from ARM, and we build the NOC, okay, the network on chip. And we built also the C2C bus, which connect the CPU to the GPU. Now, the C2C has its own performance counter, but these are specific to NVIDIA. So unless you have the Grace system, those are the counter makes no sense. So we could stream them in PAPI, but if you don't have a Grace system, it's basically void. So one will upstream them at some point in time, but these are very specific. So for Grace, use the profiler that you like. If you care about only Grace, use the profiler that you like the most. If you are developing a GPU application on Grace software, it's good to use our tool because not only the CPU side, you can see performance counter, but you can see the C2C performance counter that can give you an idea, for example, about how much traffic goes through the C2C, how much.
To clarify, the reason that I meant it as a provocative question is that we are also considering different types of ARM CPUs together with NVIDIA GPUs. And I was wondering if we could still use the same profiler toolset. But from what I understand, we should be able to.
Yeah, definitely. If you pair a GPU, definitely, it's going to work. Yeah, it's going to work. And on this point, I would love to make sure that we as a company, we don't really bet on ARM just with Grace software. We build Grace software for specific reasons, but we still work with Ampere computing, we still work with Graviton, we still work, hopefully in the future, with Cyperl, they build their CPU, to basically enable GPUs to work on any ARC64, V8 and V9 type of architecture. So people can have choice. At the same time, we continue to build GPU that goes on x86. So this is just to be clear on that. We just don't care. We care about Grace, but we care about ARM in general as a differentiator compared to the x86 core.
Okay, thanks a lot.
Okay, I understand, Filippo, you have to run to pick up your son. So
yeah, exactly.
Yeah, I think we need to stop here, unfortunately. And yeah, thank you very much again for giving this very nice talk, and see you soon.
Thanks for the time.